purpose. And in between, he worked as an instrumentation and control engineer with General Electric in Hyderabad from 2008 to 2010. In 2012, he joined Monash University, Australia, for pursuing PhD in Nanophotonic engineering. He completed his PhD in 2015 and joined the Nanoplasmonic research group at the Imperial College London, UK, as postdoctoral research associate. Since mid-2017, he is working as an assistant professor in the Department of Electronics and Electrical Engineering at Indian Institute of Technology, Guwahati. His research area includes plasmonics and metamaterials, smart electro-tunable nanophotonic devices, nanophotonic with deep learning, high-speed electro-optic modules, ENZ metamaterials, magnetic metamaterials for MRI. Dr. Sigdar was offered the prestigious Victoria India Doctoral Scholarship in 2012 for pursuing PhD in engineering at Monash University, Australia. He was awarded with the prestigious Douglas Lampert Electrical Engineering Research Prize and Medal in 2016 for the best PhD thesis in Department of ECSE, Monash University. He was also awarded the Marie Curie Individual Fellowship for developing smart electro-tunable optical metamaterial at Imperial College London. He is a member of IEEE Photonic Society, Optical Society of America, and Optical Society of India. He has published more than 700 journals of international repute in the high-impact journals and having 1400 plus citation. He is also the author of one of the PCT patent. So I hand over to you. We welcome you all, Dr. Sigdar, for having for sharing this knowledge, your knowledge with us. Now over to you.
Thank you, madam, for this generous introduction. And it's my privilege to get this opportunity to share my findings with all of you through this online platform. So I heartily congratulate all of you who have organized this particular session and all these wonderful lectures. I didn't get the opportunity to listen to previous speakers, but I'm sure they might have done a tremendous job. So I'm also trying to bring something to you that is a bit new, and that is what I am passionate about doing. So that is what my topic of today's. I'll be talking about smart electro-tunable nanophotonic devices. Okay, and this is a part of work that I have done after my PhD, and I'm still continuing in this area because there is a lot of scope. And when we try to go into this particular area, we first need to understand what is nanophotonic devices or what is nanophotonics. So if someone thinks about nanophotonics or simply say nano-optics, this is basically the study of the behavior of light on the nanometer scale, or you can say it is about the interaction of light with any nanometer scale objects. Now, it is a true multidisciplinary research area because it's a branch of optics, optical engineering, electrical engineering, and nanotechnology. And it often, but not exclusively, involves metallic components which can transport and focus light via surface plasmon polaritops. Now, there are a couple of new terms here, so we will try to come across what are these. But what is the application window we are talking about? So just like optics, nano-optics also deals with ultraviolet, visible, and near infrared. So we are basically talking about applications in free space wavelengths from 300 to 1600 nanometer range, roughly. Now, the question is why we are interested in this research area. What is new and what is the requirement? Now, this particular slide will give you an overview of where we are heading to. So this basically gives us the motivation behind this research. Now, if you look into the global internet trend, so from 2017 to 2022, you can see the number of internet users, they are jumping to 4.8 billion. More number of devices getting connected. People require more, speed for downloading and uploading, and there are more traffic, data traffic. So these requirements are the motivation behind this particular research. Now, why we need to go into plasmonics? What is wrong with photonics or electronics? Okay. Now, this particular graph here will give you an overview of where exactly each of this technology is standing. So if you look into semiconductor electronics, they have done very good towards miniaturization of the device. That is why you are seeing electronic components getting lighter and smaller day by day. Okay, but then there is a restriction towards the operating speed, which is typically limited by the RC delay of the circuits. So you cannot actually infinitely increase your speed of the semiconductor electronic devices. You cannot make them work in terahertz speed. On the other hand, if you think about photonics, there you actually can do a lot of stuff at the speed of light. So you can actually do communication at the speed of light. So you are able to increase your operating speed. But then there is a restriction in photonics. In photonics, you cannot make your device smaller than the diffraction limit of light. Okay, so that is where dielectric photonics is having its bottleneck. So we want something to fill in this particular gap, where you can have device as miniaturized as your electronic components these days, but they should actually work at the speed of light. So this is the motivation behind moving towards plasmonics. So to transport huge amount of data at a high speed, along with miniaturization, both of these existing technologies, they are facing limitations. And this is where we want to look for alternative technology. So one way ahead is that we can extend optoelectronics into nanometer scale, but in that case, we have to convert photons or light into plasmons. Now, what are plasmons? Plasmons are basically electron waves. And this particular technology, which has been pioneered, is called plasmonics or metallic nanoplasmonics. So plasmons are having much shorter wavelength than light, and they are able to propagate electronic signals. So shorter wavelength allows you the miniaturization of the device, which photonic devices were not able to achieve. So this is the solution for both the bottlenecks faced by semiconductor electronics and dielectric photonics. And plasmonics will enable an improved synergy between electronic and photonic device, because these plasmonic devices, they have similar dimension of the electronic components, and they can naturally interface with similar operating speed of the photonic network. So they are the solutions going ahead. Now, when we talk about plasmonics, we understood that plasmonics merges photonics and electronics at nanoscale, and it has become one of the most important growth areas for this century. And it allows us to investigate electron oscillations in metallic nanostructures and nanoparticles. However, if you look into the physics perspective, plasmonics basically deal in the generation, manipulation, and detection of surface plasmon polaritons, or SPPs. So when you say SPPs, these are basically quasi-particles which are there because of coupling of light and surface plasmon. And what is surface plasmon? I just told that these are basically electron oscillation wave at metal surfaces. So this is a young and promising topic, and this is basically a branch of nanophotonics. So today our lecture will be mainly based on smart nanoplasmonic devices, which are also tunable. Now let us go into a little bit more of plasmons and see how plasmons are generated and what plasmons basically are. So to start with, we can say that plasmon is basically a density wave in an electron gas. Just like if you think of, sound wave is basically a density wave in a gas consisting of molecules. Similarly, plasmon is basically a density wave in electron gas. And where do they exist? They will exist in metals where electrons are abundant and they are weakly bound to their atoms and free to move. The electrons in the metal, they can wobble like a piece of jelly, where they are actually pulled back by the attraction of the positive metal ion they leave behind. So if you imagine a piece of jelly and poke it with your hand, you will see wobbling. Similar kind of thing happens in metal, and this electron cloud keep on wobbling or oscillating. So plasmon is basically a collective wave where electrons, rather billions of electrons, oscillate in sync. So where do I see plasmons? How about bulk gold or bulk material or bulk metal? So bulk plasmon is something like a longitudinal wave. So this is basically oscillation of free electrons along the bulk of the metal. Now, can I excite bulk plasmon by shining light? The answer is no. Because light is basically a transverse wave and it cannot couple or transfer its energy to a longitudinal wave. So you cannot directly excite bulk plasmon. And what is the frequency of bulk plasmon or plasma? It's given as omega p, which is square root of n e squared by m epsilon naught. N is electron density, E is electronic charge, m is electronic mass, and epsilon naught is vacuum permittivity. So as you can understand that this is basically a property of the metal itself. Okay. And how do you define plasma frequency? It's the frequency beyond which metals become transparent. How about surface plasmons? So this is bulk plasmon and this one is surface plasmon. So it is very clear that the surface plasmon exists at the boundary between metal and dielectric. So if you think of a metal dielectric interface, and if you think of evanescent waves, you'll see that the waves are penetrating more into the dielectric side, but they are actually propagating along the interface. And this is called surface plasmon polariton. And this is basically a propagating surface wave, and it's not a localized resonance. And where does it exist? It exists along metal dielectric interface. And does it happen in every condition? The answer is no. You have to, satisfy certain conditions and you can get this surface plasma frequency. So as you can see, the resonance frequency omega sp depends on omega p over square root of 1 plus epsilon d. So here epsilon d, the choice of the dielectric, plays a role in deciding the surface plasmon frequency. And what is omega p? That is the property of the metal, which we cannot change, right? Now, are we able to excite surface plasmon polaritons straight away on a metal dielectric interface? The answer is again no. The reason is there is a phase mismatch between photons and plasmons. So if you look into this black straight line, this actually is the light line or the dispersion curve of a photon in vacuum. Omega equals Ck. Okay, and this is the beta. Okay, so beta is the propagation constant of surface plasmon, which is given as omega over c square root of epsilon d epsilon m over epsilon d plus epsilon m. I'm not going into the derivation of this, but this particular graph is basically the omega SP over omega P. Okay, so this is nothing but 1 over square root 1 plus epsilon D, and that is why it is getting saturated. Okay, so in this particular diagram, you can see that there is no phase mismatch. There is no phase matching. So there is no phase matching means there is no energy transfer or momentum transfer that is happening. So what you have to do, you can actually use a geometry called Kretschmann configuration like this. So this is your metallic film, and you place your metallic film on top of a glass prism, and there you shine light from the glass side. So what happens, because of this dielectric permittivity of the glass, you can reduce the slope of this black line to this blue line. We all know that omega equals ck is the dispersion relation in a photon in vacuum or air, and when it goes inside any material with refractive index n, it becomes omega equals c by nk. So the slope basically reduces, and this blue line is the new dispersion relation of photon in this particular glass prism. After that, you can actually manipulate or tune this incident angle so that the horizontal component of the propagation vector or the momentum matches with that of the surface plasmon, and this is what it is doing. You see, you can choose your theta such that this blue line exactly gives you the same value, okay, of momentum, okay, for the SPPs also. So that is where you will be able to couple surface plasmon polaritons, or you will be able to surface plasmon polaritons at metal air interface. But will you be able to do it in the metal dielectric interface? Because here you see there are basically two interfaces. One is metal dielectric, another is metal air interface. But if you look into this equation, okay, so here you see this curve is the dispersion relation for metal dielectric SPP. So you will not be able to couple this photon or this plasmon from this particular photon, because all of these are already having much higher momentum than your photons. So this coupling of SPPs at metal dielectric interface is not possible, but you will be able to excite surface plasmon polaritons at metal air interface. That is doable. So as you can understand that exciting SPPs at metal dielectric interface or metal air interface is a bit tricky stuff. So how about localized surface plasmon? Now, what is localized surface plasmon doing? That gives you hassle-free direct excitation of plasmons. And how it happens? You take a nanoparticle or a curved surface which has got a finite volume. Okay, so what happens when light falls on it? Depending on the electric field, the electron cloud is pushed on the other side. So this is the electron cloud pushed downward because of the electric field. And when the electric field is changing direction, the electron cloud is also changing direction. So what is happening? The electron cloud is basically oscillating with the frequency of this electric field. That is electric field of the light. Now, if that frequency matches the frequency of the plasmons of the metal, there will be a resonance. Okay, and this is where you get localized surface plasmon resonance. So what is good thing about localized surface plasmon resonance or LSPR? You can directly excite them using light illumination. You do not need any bulky arrangement like Kretschmann or other configurations to make momentum matching happen. It can actually work directly. The other one is resonance enhanced absorption and scattering of incident light. So you actually can have much larger cross-section, scattering cross-section or absorption cross-section of your nanoparticle than their geometric cross-section. You can obtain very strong, confinement of electric field in or around the particle, and this resonance is sensitive to the nanoparticles' shape, size, composition, and the permittivity of the surrounding. Now, why these things are interesting? Because you see that there is a charge separation happening here. So these nanoparticles, upon light excitation, they behave like dipole. And when you have this oscillating electric field, this dipole is also oscillating. So it becomes like a nano antenna. Okay, that is where this field, this particular localized surface plasmon resonance becomes very interesting. But another interesting fact is that this particle plasmon right museum. When you shine light from the outside, the cup appears blue green. Okay, but when you shine light from inside, the cup appears red. So the reason is, when you see the reflection, this is basically the scattering resonance of the nanoparticles which are embedded in the glass, and they resonate at blue green. So you see it like this, and when the light source is inside, blue green is getting absorbed. So white light minus blue green is red, and that is why you see red. It means their absorption cross-section or absorption resonance is also at blue green. So this is where your nanoparticles can actually give you some very interesting phenomena. Now, how do we describe these nanoparticles? That are very standard and easy theory that can handle these nanoparticles. I'll not go into much details. I'll just show you that very simple theory can also handle these nanoparticles. So if your nanoparticles are much smaller than the wavelength of the light that you are working with, you can assume that the electromagnetic field is basically constant over the particle volume. So in that case, you can assume that electrostatic approximation is valid. Okay, so you can simply solve Laplace equation, okay, and obtain what is the potential inside and outside the nanoparticle. And when you obtain the expression for the potential that is outside the nanoparticle, you will see that there is a component. This is the incident electric field, and there is something new coming up here. Okay, so what is this term? P dot R, okay, over 4 pi epsilon naught epsilon d r cube. So this is basically the polarization of the dipole that is getting created. Okay, and you can express this using epsilon d alpha epsilon naught, where alpha is the polarizability of the particle. Now, for a simple spherical nanoparticle, if you look into the expression for alpha, it has got these terms, epsilon m minus epsilon d, that is the metal permittivity, d is the dielectric permittivity. And when there will be a resonance, there will be a resonance when the denominator of this goes to 0. So that is known as Froelich condition. And when you plot alpha as a function of omega over omega p, you will see that when gamma is basically the damping, that is the loss in the metal. When gamma is increasing, the resonance is getting weaker and broader. And that is what happens for all resonators, that the quality factor of the resonance goes down. Okay, so this basically tells you that you can approximate a tiny nanoparticle using a simple quasi-static approximation, and you can obtain what is polarizability alpha. And once you obtain alpha, your life becomes very easy, because you can calculate scattering cross-section and absorption cross-section using these very simple formulas. And then that can give you extinction cross-section as well. So they tell you a lot about, the characteristics that scattering cross-section scales as 6 power of alpha, or sorry, A, which is the radius of the particle, whereas, absorption cross-section scales as A cube. It means when the particle is small, absorption will dominate, but as your particle keep on increasing in size, scattering will dominate. So you can actually understand that based on your requirement, you can design nano antennas which can scatter or absorb light. Okay. So this is another illustration that tells you that if the refractive index of the surrounding media changes, there is a shift in resonance peak because your epsilon d is changing. Now, if you compare bulk, surface, and particle plasmons, what we saw that the condition for bulk plasmon is this, where the permittivity becomes 0 at that frequency. That is the frequency of bulk plasmon resonance. Surface plasmon resonance, this is the equation, and for particle plasmon resonance, this is the equation. It means you can also obtain what is the bulk plasma frequency, omega p, omega sp, and omega LSPR. So what you see here, that the bulk plasma frequency is basically a pure metallic property, and that is why these are all fixed. So silver has got this property. It has got a plasma frequency of 9.6 electron volt, which is around 129 nanometer. Gold has got 8.6 eV, which is around 144 nanometer. And copper has got 7.4 eV, which is 167 nanometer. But surface plasmons, the frequency is tunable. You can change epsilon d and can shift it towards red. And you can see here, based on the Froelich condition we have seen before, the localized surface plasmon frequency can be further brought down. The frequency is getting down, the wavelength is getting redshifted. So you can slowly push them towards, visible and near infrared wavelengths. And what about the tunability? Yes. The resonance is tunable with the size of the nanoparticles. So if you take, different sizes, you can see that for gold nanoparticle and silver nanoparticle, you can have resonances ranging from up to 600 or 660 nanometer. These are the ranges supported by silver and gold nanospheres. If you look for other shapes other than nanospheres like nanoshell or nanoegg, nanorods, triangles, cubes, nanorice, you can actually cover almost, starting from UV, you can cover visible, you can cover infrared, and up to mid-infrared. So that is a lot of tunability that you get from this localized surface plasmon resonances. So that is why they are particularly very interesting. And one particular example here is that if you have a gold, if you have a nano antenna that is made of silica core coated with gold, so this one has got a gold shell thickness of 20 nanometer. The resonance is here around 740, 730. And when the shell thickness reduces to 5 nanometer, you see you can move the resonance to 1000 nanometer plus. So that is one example of how tunable these resonances are. So based on your application, you can choose the shape and size of the nanoparticles. Another important aspect is that what are the different methods, numerical methods available for computing these optical responses of the nanoantennas. One very standard method is called Mie theory, and that has been solved by Gustav Mie in 1908. It's a very standard theory that allows you to calculate the scattering and absorption cross-section for spherical nanoparticles. Okay, but this doesn't apply to nanoparticles which are of different shape, or even for nanoparticles which are close to substrate. So they are not very good for describing any experimental situation. You can also use T-matrix methods, transfer matrix methods, where you can computationally solve the boundary conditions for different layers, and you can actually go and make it for different shape objects. But again, they can become computationally unstable for flattened objects or elongated objects. Then there is discrete dipole approximation, which is shown here. So you can approximate any shape nanoparticle as an 3D array of dipoles. But then again, there is a convergence criteria given, which is modulus of nkd should be less than 1, where n is the complex refractive index. Okay? And k and d are the wave vector and the interdipole separation. Other computational methods, which are basically now very popular, that is FEM, finite element method, and FDTD, finite difference time domain method. So FEM is a frequency domain technique, and this is a time domain technique, FDTD. There you can actually solve for any complex shape nanoparticle, and you can obtain the scattering and absorption cross-section of nanoparticles. So what are the applications of plasmonic nanoparticles? As I mentioned, they can be used for nanoscale devices and circuits. They are very useful in plasmonic solar cells, where they can absorb incident solar radiation much more effectively. Biomedical applications like this, where nanoparticles can absorb near-infrared light, and when they are placed on top of a cancer cell, they can get heated up and kill cancer cells locally. They can be used for biological and chemical sensing because of the strong near-field confinement around the nanoparticles. They can actually significantly enhance the Raman scattering signatures of any molecule present near them. So that field is very popular. It's called SERS, surface enhanced Raman scattering. You can use them for optical data storage, optical nano antenna. You can also use them for maskless fabrication technology, where you can place your nanoparticles and shine light on them, where the nanoparticles absorb light, get heated up, and melt to make those wires and wire. Okay. So these are different applications of plasmonic nanoparticles. So let me take you to one example of optical nano switch, how you can design an optical nano switch based on plasmonics. So let us consider one nanoparticle, which is basically a gold dielectric gold nanosphere. So it's a 3-layer system. And again, you can use quasi-static approximation to solve for electric potential in each region. And there you can apply continuity of the tangential component of electric field and the normal component of the displacement field at each layer, and that will give you the polarizability expressions. The final expression would be like the polarizability is epsilon4 alpha and then electric field which is incident. So when you do the calculation, you can obtain the polarizability alpha of the nanoparticle. So as you can see here, it depends mostly on the material permittivities and the dimension of the nanoparticles. And once you obtain the polarizability, your technique is very straightforward. You can obtain scattering cross-section straight from this particular formula. So if you look into the alpha expression, okay, alpha has got a numerator and denominator. So when the denominator goes to 0, you get a scattering resonance. So it's a high scattering state. But when the numerator goes to 0, you get a low scattering state or a cloak state. So if we obtain those expressions explicitly, that where scattering resonance is taking place and where cloaking resonance is taking place, so you obtain these two conditions. And then you can plot them as a function of physical parameters. P is nothing but R1 over R3. R1 is the core radius, R3 is the outer radius, and Q is nothing but R2 over R3, which is the radius of the dielectric layer over the outer radius. And what are the red curves here? The red curves shows you scattering resonance. The blue one shows you cloak state or low scattering state. So one interesting feature is where this high and low scattering states are getting merged is it means at that particular, and this is wavelength, okay? So it means that at that particular wavelength, this high and low scattering states are very close to each other. So you can switch between them by slightly changing the incident light wavelength. And what is shown here is that at different dimensions of this three-layer structure, you can obtain many such conditions where high and low scattering states are getting merged. Now, life comes with some difficulties. Similarly, all these metallic structures, they will come with some losses. So when you consider the losses in your calculations, you see that those sharp dips and peaks, they are getting disappeared. They're all getting broad, and the deep is getting shallower, peak is also getting shorter. So to restore such good performance, what you have seen here, this is basically done in lossless regime where we consider metal to be lossless. So when you come back and consider the metal in its original form, that the metal is lossy, but then you do something to incorporate that loss or compensate that loss. You put some quantum dot inside the dielectric layer so that there is some gain. So in that case, you find this kind of compensation, and you will see that you are able to restore those high peak and low dips. So let us take one example here, L2 and H2. You can see H2 happens at 595 nanometer wavelength, and the normalized scattering is 0. And L2 happens at 577, and the normalized scattering is minus 88 dB. That means with just change of 18 nanometer of wavelength of the incident light, you can get a contrast of high and low scattering state by 88 dB. So what does it mean physically? This is how the nanoparticle or the nano antenna will behave. When you shine a 595 nanometer wavelength, it behaves like a proper scatterer. It has got a very strong electric field in and around the particle. But as in contrast to it, when you see 577, you can see that the outside is as normal as if there is no nanoparticle. So this nanoparticle is basically in a cloaked state or in a off state. It has concentrated all its electric field inside the dielectric layer. So this is the high contrast regime. So you can use this nanoparticle at 595 nanometer as on switch, and this you can use as off switch. So this is how you can design very high speed scattering switching based on nanoparticles. Now moving on to plasmonic metamaterial devices, where you have many such nanoparticles forming a 2D array which is basically sub-wavelength in size. Now, what do you mean by sub-wavelength? That each nanoparticle is also much smaller than the wavelength of light, and the interparticle separation is also much smaller. So what happens? These nanoparticles can effectively behave like a different or a unique layer, and it has a very different metallic property than the constituent material. And one good thing is that they not only give extraordinary optical properties, they can also be efficiently created by self-assembly of nanoparticles. So you do not need to do top-down fabrication. You can use very inexpensive methodology of self-assembly. Now, what are the problems with this kind of devices if you make? They're typically not having any in situ control. Means once you have made this device, they are all fixed. They will not change, right? So this is where things get interesting if we make them smart optical metamaterials. Now, how do we introduce electrotunability in their optical properties so that they give you first adjustable and reversible in situ control? So I'll show you the means of doing this in this lecture. Meanwhile, I'll also tell you what are the applications. So they have numerous applications in tunable optics where you can quickly switch from a window or a mirror state, or you can switch from a mirror and absorber state. Now, why I'm calling it mirror? Because when these nanoparticles are getting very close packed, they effectively behave like a thin metallic layer. Now, if you take gold metal, though that new metallic layer they are forming effectively, that will have a very different refractive index or permittivity than original gold, but that layer will still have very good reflectivity. So a dense nanoparticle layer of gold nanoparticles basically can be thought of a mirror, and a sparse layer can be thought of a window where light can simply pass through. Okay, they can be used for smart energy harvesting. So depending on the frequency or the wavelength of light that you want to reflect, you can reflect. The one you want to transmit, you can transmit. Okay, you can also use them for programmable optical filters and cavities, which I'll try to show you today. And they are also very good hotspot for sensing application. So all of this, nanoparticles will have very strong electric field near them. So you can use them for biological or chemical sensing. So this field of smart optical metamaterial devices, it is basically a, mixed, or it's basically a merger of nanoplasmonics, physical chemistry, electrochemistry, optics, and engineering. And these devices are something like, I took this from that movie Robo. I believe everybody have watched this. So if you have seen this movie, you could have seen that these robots can be instructed to form any structure. They can form any shape and they can have any property. Similarly, the nanoparticles can also be instructed to form any shape structure to give you the unique optical properties or response that you want. So you can use template electrodes to assist their formation of different structures. So I'll show that in the next few slides. So let us first have a look at how these metamaterials are formed at liquid-liquid interface. So if you take a oil-water interface and you take gold nanoparticles which are capped with ligands, okay? So these are some kind of polymers, and when you put these nanoparticles in the electrolytic solution, these ligands acquire negative charges. So what happens? All these gold nanoparticles will acquire negative charges and they will try to repel each other. Now, depending on how much are the negative charges on them, that will decide their interparticle separation. Now there is another force that works very strong in nano regime, that is van der Waals attraction. So there are two competing forces here. One is van der Waals attraction, another one is this electrostatic repulsion. So based on the fine tuning of these two opposing forces, you can ensure that you are able to make a layer or a dense layer of nanoparticle that behaves in the way you want. So if you look into this, normal structure, this is a oil-water interface where, you can have nanoparticles. If the separation is large, they behave like a weak mirror. You see there is a candle hold which we put next to it and you see a weak reflection. But when there are more nanoparticles in this interface, the interface becomes like a strong mirror and you see a very strong reflection. Now, what is the problem in that system? That is not electrotunable. So let us try to make a reversible system where you can use electrodes in the aqueous and organic phase. So organic phase is the oil phase, aqueous phase is the water phase, and the nanoparticles are having negative charge. So if the electrode in the water phase has got negative polarity, you are basically pushing all the nanoparticles toward the interface where they will try to, populate the interface and form a dense layer. So this is the case where it, the interface will behave like a mirror. But when you reverse the polarity, that is when you make water phase positive, you actually attract all the nanoparticles towards the electrode. So all the nanoparticles will depopulate your interface and it will become transparent like a window. So this is one example of a mirror that is formed. So this is the reflection. This is the actual mirror that is formed at the water oil interface by the nanoparticles. You can see how good mirror this is. And there, if you apply the potential, you can actually construct or destruct the mirror. And another interesting part is that by slowly varying the potential, you can also control the reflectivity of this mirror that is getting formed. And you can see we are able to predict this using both experiment theory, and we understand how things work in this particular regime. So basically, when the nanoparticles are getting close to each other, they are forming a fictitious film of a effective permittivity, which is slightly different than gold, but that layer reflects very strong. And you can repeat this assembly, disassembly process of nanoparticles many times, and you will see that they actually, repeat the performance. So it's a very stable system. So this is an experimental setup where you put a coin at the top and a banknote at the bottom. So this research was done in Imperial College, which was published in Metamaterials. And there we see that, this is the window state. So you're able to see the coin, the 10-pound note at the bottom, and the coin is at the top. And slowly, when you turn in the voltage, the mirror is getting formed. So you are starting to see the reflection of the coin. And this is where you see a very strong reflection of the coin because the mirror state is completely formed. Okay. Now the question lies how to model this kind of systems. So there are many existing theories that help you to model this. Sorry. Okay. So there are many existing theories which I don't know how to get rid of this. Okay, it's here. Okay. So there are many existing theories like Maxwell-Garnett, Brugman, and Laird. So these theories allow you to approximate the permittivity of a composite medium. So in this particular case, Maxwell-Garnett, you can actually have very distinct grain structure. It means if you have nanoparticles dispersed in some media, you can use this theory. Okay. And there what is considered is the, if you consider this volume fraction that is populated by the nanoparticle as F, you can calculate what is the effective refractive index of this or effective permittivity of this mixed structure. Brugman configuration also does something very similar, but in this case you have aggregate structure. So you do not have a very separated grain structure like Maxwell-Garnett. So here what happens, in the effective medium theory, you actually can have the permittivity by assuming that F is the probability of that particular material being A. And 1 minus F is the probability of that material being B. So if you take that into consideration, this equation gives you epsilon effective, which is the effective permittivity of this kind of structure. When you have a multi-layered structure, which is periodically repeating like high, low, and you can have electric field which is along the interface or perpendicular to the interface. So you can have two cases where in this case the capacitance is basically proportional to the thickness of the layers, and here it is inversely proportional to the thickness of the layers. And there you can obtain what is epsilon parallel and epsilon perpendicular for this kind of anisotropic materials. So one direct application of this kind of theory would be hyperbolic metamaterials, where you have alternating structures of metal and dielectric. Now coming back to our structure, where we have nanoparticle layers. So our main objective is to represent this nanoparticle layer as a layer of a fictitious material, but it should be a homogeneous and continuous layer, not a discrete structure. So we need to find out what is the effective polarizability of each nanoparticle in the presence of all other nanoparticles and the image that is formed in this interface. So this is a illustration of different coupling. So there is coupling. Let us take the center nanoparticle. It is getting coupled from the nanoparticles on the sides, from its own image, from the image of the neighbors and of the same row or adjacent rows. And when you compute all these interactions together, you will see that you are able to find out what is beta parallel and beta perpendicular. So these are the effective permittivities, effective polarizabilities of the nanoparticles in each of these layers. And once you know that, you can obtain what will be the epsilon parallel and epsilon perpendicular for this layer. And then you apply transfer matrix method, where M1, M2, M3 are basically the different layers that is there. So each matrix will present one interface, and that is how you can get a overall transfer matrix for this entire system. And once you obtain that overall transfer matrix, you can find out what is the element M21, and you divide it by M11. That will give you reflection coefficient for this entire geometry. So this is how you can obtain the optical response, like reflection and transmission, from transfer matrix method and effective medium theory. Now there are a couple of very fundamental theories which also apply for handling this. So one is Frannel theory, because Frannel tells you that how to compute reflection and transmission coefficient when your light is hitting an interface. I'll not go into the details of this, but I'll just give you one example of what happens in S polarization case. So this is S polarization case, where the electric field is striking out of the plane of this paper or plane of this your computer screen. And you see this is the magnetic field vectors. So what are the boundary conditions that you have to apply at the interface? That the tangential electric field is continuous. So what is that? EI at y equals 0 plus ER at y equals 0 should be equal to ET at y equals 0. So that is how the electric field continuity works. How about magnetic field? There also we say that the tangential magnetic field is continuous. So tangential field, because magnetic field direction is this way, so you have to find out what is the direction along the interface. So here you can see this is minus bi, cos theta I, and then you put them at y equals 0. This one br cos theta r at y equals 0 should be equal to minus bt at y equals 0 and then cos theta t. And why we are dealing with B, that is the magnetic flux, not the magnetic field, because you can also do it for B by a mu. That will be exactly same, because all mu's here are 1. We consider all materials as non-magnetic, right? So after you do that, you can use these equations and obtain what is the ratio of the reflected electric field over the incident electric field, that is your reflection coefficient, and what is the ratio of the transmitted electric field over the incident electric field, that is your transmission coefficient. And once you obtain both these coefficients, you can also repeat the same exercise for plane polarized light or TM polarized light, and you will obtain the equations of R parallel and T parallel. So these are basically reflection and transmission coefficients. So this is the summary of both reflection and transmission coefficients. Now from that, what we are able to obtain? We are able to obtain what is reflectance. That is reflected power over incident power. Now reflected power is IR AR over IA AI. Okay. So here you see the beam width is remaining same, so the area will remain same, and you can obtain reflectance as square of reflection coefficient. However, because in transmittance there are two different medium, the beam width will change because the angle is also changing. Okay, and in that case, your transmission depends on transmittance depends on transmission coefficient square and this ratio nt cos theta t over n I cos theta I. Okay, the derivation is here. It is nothing but the ratio of transmitted power over incident power. It's very straightforward, and this is what we get. So always remember that small r plus small t gives you 1. Okay, that is not always true. So the coefficients do not always add up to 1, but reflectance and transmittance in a non-absorbing system should be equal to 1. Okay. Then there is another method which I briefly discussed, with the transfer matrix method that you can utilize for multi-layer system. So in multi-layer system, what happens? You can consider different layer to have different refractive index like this, N0, N1, N2, and Nn. And these are different, dimension. So x less than x0, x0. So you have n0. So this is your n0, that is here. Then when x is between x0 and x1, you have this material which is got n1 and so on. So you can actually define all these different materials and what are their interface planes like this. Then you can also write down the forward electric field on the back side of the interface, that is xi minus. What is the backward propagating electric field, that is EB on the left side of the interface, xi minus. You have EF xi plus and EB xi plus. Okay, and then there is another concept also. What happens when the electric field enters one layer? So this is what happens at the interface between Ni and Nj. This is what happens when electric field or light enters your media Ni. So you have like this. So you have EF xi minus 1 plus. So the electric here. Then you have electric field here, which is EF xi minus. At this point, it will be reflected. So it is backward propagating EB xi minus. And here it is EB xi minus 1 plus. So what are these? These are the different electric fields and how they will be related, because they are traveling inside one particular medium. So only difference would be the phase. But here you have to match the boundary conditions to find out the relationship between each of these different components. And that is where exactly the transfer matrix works. So this is the transfer matrix for one interface. I'll not go into much details. I'll just show you the result. So this is how you can relate the electric field on the left side of the interface to the electric field on the right side of the interface, and this will be the transfer matrix. Tij, Rij. What are these Tij, Rij? These are the reflection and transmission coefficient which we got from Frannel theory. Okay. So for one interface, you can simply use this particular transfer matrix. Okay. So this is the transfer matrix for one interface. How about one layer? When you enter a layer, as I mentioned, you will only have a phase difference between this and this. So that is named as phi d, okay, phi I, which is kxi di. Now kxi di is nothing but the kxi is the propagation constant, and di is the optical length that it travels. So it is not this length, it will be along the direction of the propagation. So it will be AB prime. So you can write phi I equals kxi di equals 2 pi over lambda naught ni di cos theta I. Okay. So what we are doing here, it is basically giving you, the properties of a particular layer. So when you have multiple layers and multiple interfaces, your overall transfer matrix will be T0n. It means it will start from 0, 1, that is one interface. Then you will have another transfer matrix T1, that will be the transfer matrix of layer 1. Then you enter the interface, then you come across the interface between layer 1 and 2. So it is given as T12. Then you enter layer 2. So that is given as T2, and so on. And each of these transfer matrices you already know from Frannel reflection coefficients. So it is just plug and play. And then when you do the matrix multiplication, you can obtain the overall properties of the entire system. Okay. And once you obtain the overall properties of the system, you take the element number 2, 1 and divide it by element number 1, 1. You will get the reflection coefficient. And if you simply take the inverse of the element number 1, 1, you get the transmission coefficient. And once again, from that, if you want reflectance, which is the reflected power over incident power, you can simply take the modular square of that coefficient. And if you want transmittance, capital T, you can obtain it using this formula. So I hope it is clear how we can handle the optical propagation properties in a multi-layer stack system. And we can always verify all of this by taking simulation model like COMSOL, CST helps you simulate all these structures. Now if I go back to my structure where there are nanoparticles forming 2D arrays, so spherical nanoparticles typically aim to make hexagonal arrays, because that will give them minimum entropy, because all the nanoparticles will have equidistant neighbors. So how do you model this kind of system? You can take a unit cell in this particular rectangular shape. So this is the unit cell, and out of symmetry you can only simulate 1/2 of it. And then this is the YZ view of the simulation model. And once you apply the periodic boundary conditions at this unit cell, we'll be able to replicate what is happening in this two-dimensional array, right? So going back to the application, we have already seen that this allows you to make reversible, window mirror system at liquid-liquid interface, right? Now, when you go and make the system on a solid liquid interface, it means you have a silver substrate which you are now using as a negative electrode, and then you have a gold nanoparticle solution, and you keep an electrode which is a positive electrode. And these nanoparticles, like before, they are negatively charged. So when water is positively charged and the nanoparticles are negatively charged, they are all swimming or floating in the water layer. So what will happen? You can shine light, and the light will hit the bare silver surface, and you will get complete reflection, like 99% reflectivity that you typically get from a silver mirror. But as soon as you alter the electrode potential, that is, you make your silver electrode a positive electrode, all these nanoparticles will come and settle down, and they will form a 2D array. And this 2D array will be able to absorb your incident radiation, and you will get almost zero reflection. And this system is basically a reversible system, as you can understand. If you alter the potential, you can quickly change the system from a mirror to an absorber. So again, how do you do the theoretical modeling of this? As I mentioned, the effective medium theory, where you can take this nanoparticle layer and try to model is this as this layer 2, which is a fictitious layer but a uniform layer of a permittivity that is derived from our effective medium theory, where I have shown you the calculation of beta parallel and beta perpendicular. From that, you can obtain what is epsilon parallel and epsilon perpendicular. And once you obtain that, this is a very easy multi-layer system. So you can use transfer matrix method here, right? And what you will do, you will have how many interfaces you have? You have interface here 1, 2, then you have interface 2, 3, you have interface 3, 4, you have interface 4, 5. How many layers you have? Layer 2, layer 3, layer 4, right? And now when you put all these matrices in the proper order and simply multiply them, from the overall matrix, you can obtain what is reflection coefficient, what is transmission coefficient, and you can plot it. So this is what we have shown here. So when you see this is the reflectance curve. So when there is only silver film and there is no nanoparticle anywhere, you'll see you get very strong reflection. You get almost 99% of reflection. But if you bring nanoparticles, which are gold nanoparticles of say 10 nanometer of radius and interparticle spacing of 4 nanometer, they're very dense packed, and you see the reflection curve gets very strong dip. The solid ones are from simulation. Sorry, the solid one is from this theory, and the dotted one is from COMSOL simulation. And you see that these two are very close to each other. We are able to predict this feature from our effective medium theory. So what is happening at this particular wavelength is very, very interesting, because when there is no nanoparticle, you have 99% of reflection. When nanoparticles assemble, you get 0% of reflection. So you're able to switch between a perfect reflector and a perfect absorber. And good thing is that by changing the size and the interparticle gap of the nanoparticles, you can actually change the wavelength of operation of this device. So here you are operating at around 630. Here, by changing the nanoparticles, you can bring the dip somewhere here. So here you are operating at around 580. So you can have this feature anywhere in the spectrum depending on your choice of nanoparticles. Okay. This is the experimental verification of this. So when we did experiments, it was very similar setups. You have silver substrate, but now to protect the silver from oxidization, 5 nanometer titanium nitride film was deposited. So this is just a protective layer, and these are the gold nanoparticles in the 2 different phases. And you see, when low potential is applied to the electrodes, okay, so nanoparticles are not attracted towards the silver substrate. So you get a silver substrate giving you a very good reflectivity, almost 90, 95, 96%. Or here it is something around say 92% or so. Okay. And then when you keep on increasing the potential to say 0.7 volt, more number of nanoparticles, gold nanoparticles, come and sit on this silver substrate, and you see a dip in the reflectivity. And this is where you can switch between a highly reflective state to a low reflective state or a absorber state just by changing your potential from 0.1 volt to 0.7 volt. And this is what happens practically. You see, pristine silver, it is very reflective, but it has got a titanium nitride, so it is giving bit of golden reflection. Titanium nitride looks like gold. Okay, and then slowly when you have you are increasing the potential, some nanoparticles are coming and sitting. You increase to 0.5, more nanoparticles. See, These white dots are nothing but these gold nanospheres. Okay, these are the SEM images. So at 0.7 volt, you see they are very densely packed. And what has happened to your optical image of this entire setup? You see, it has turned black. Why it is black? Because it is now behaving like a absorber. Here it is a reflector, here it is an absorber. So just by changing the potential, keeping the same setup, you can change between a reflector and absorber. Another very interesting application of this kind of setup is electrically tunable Fabry-Pérot cavity. All of you might be aware that Fabry-Pérot resonant cavity has got a lot of applications in designing filters and resonators in high-speed optical communication systems. And how people make them tunable? How do you change the resonance frequency of your cavity? You have to physically alter the cavity length, or you have to modify the refractive index of the cavity filling medium. So in that case also, you have to apply very large voltage. So that sometimes does not allow you to have the device in a nanoscale circuit. So what we have proposed here is something different. We took transparent conducting oxide or thin silver electrode as substrate, and then you allow nanoparticles to sit on your cavity walls to alter the reflectivity. Okay. So let me show you what will happen. So if nanoparticles are again negatively charged, and this is a water-filled cavity, and these are the cavity walls. So when the cavity walls, these are made of TCO, transparent conducting oxide, like ITO, or you can make them with thin silver electrode. So when they are negatively charged, nanoparticles are not attracted, they are dispersed in the aqueous medium. So they will simply allow the light to pass through. Okay, so that is like the resonance cavity is off. It is not existing. It is not doing anything to the existing light. Maybe somebody can argue that what if some nanoparticles come in the path of the light? Yes, there will be slight scattering and slight absorption, but that will be really minimal. Now, what happens when you apply some positive potential to the electrodes? So then the nanoparticles will get attracted to the electrodes and they will start forming a 2D array on the electrode. And immediately the reflectivity of these cavity mirrors will change. So from transparent from transparent walls, they are now slowly becoming mirrors, and this will become like a cavity. So you are actually having a cavity in formation. So as the cavity gets formed, then this will allow only those light or those wavelengths to get transmitted, which are satisfying the Fabry-Pérot resonance condition. And by changing the reflectivity of this cavity mirror, how do you do it? You can change or increase the potential on the electrodes. You can make the mirror more denser by having more and more nanoparticles in it. So they will have a different property than this one, and that will allow you to change or tune the transmitted wavelength that is coming out from the cavity. And here we can use the Maxwell-Garnett formula, MG formula, to utilize and find out what is the effective refractive index of this cavity that has got gold nanoparticles in them. So these are the results. Now this is a cavity that is formed on thin silver substrate. Okay, and these are also not gold nanoparticles, this is silver nanoparticles because they give better response. So let us see what is happening when you have no nanoparticles. Let us assume these are the wavelengths that is coming out from the cavity, and you see these are, my theory is this one, effective medium theory, and you can also simulate the structure in COMSOL. And you can see simulation theory, they are perfect match. They're perfectly overlapping. It means the theory is able to approximate all the features of this nanophotonic device. Now, when you introduce nanoparticles in them, okay, so here these are without nanoparticles, so you can imagine this nanoparticle layer does not exist, only there is one silver mirror here and here. So this is where the cavity is. Now, if the nanoparticles are there and they are of radius 10 nanometer, gap size is 6 nanometer, you will see that this is what the transmittance wavelength look like. Sorry, transmission spectrum looks. So this peak is getting shifted by this much, this peak is getting shifted by this much, this peak is getting shifted by this much. Why this happened? This happened because if you look into the transmittance from a non-absorbing, sorry, from a absorbing Fabry-Pérot cavity, this depends on this equation, where K is dependent on 1 minus A is the absorbance, minus small r square over 1 minus small r square. What is small r? That is the reflection coefficient of the cavity mirrors. So what we are doing here is we are electrically changing the reflection coefficient of the cavity mirrors, and that is how we are able to tune the properties of this mirror and the transmission spectrum of the Fabry-Pérot resonator. So we are keeping everything same. We'll just apply potential to the electrodes, which are the silver electrodes, and that is how we will get this change in transmitted wavelength from the Fabry-Pérot cavity. So this is another illustration where the black curve shows no nanoparticle. G20 means the gap between the nanoparticles is 20. So if you apply less positive potential, the gap between the nanoparticles will be less. As you keep on increasing the electrode potential and make it more and more positive, more nanoparticles will come and sit on the electrodes, so their interparticle gap G will reduce. And when their interparticle gap G reduces, they behave like a much stronger mirror, and you will see that transmission is getting shifted towards red. Okay, so this basically gives us an idea of how to make an tunable electrochemical Fabry-Pérot cell that can be used for fast in situ electrotuning of optical transmission spectrum. Okay. Besides electrotunability, you can also change the properties by using different type of nanoparticles. And this is based on a bottom-up approach, so they are very easy to fabricate and program, and they are also energy efficient. Okay. And one more idea I would like to share with you, that these nanoparticles are also very useful in improving the light extraction efficiency from light emitting diodes. And you can understand, in today's communication world and overall in overall electronics industry, LEDs are always in high demand, and there are a lot of applications of these LEDs, right? So if we are able to extract more light from these LEDs using nanoparticle metagrid, which is nothing but a 2D layer of nanoparticles, then it would be wonderful. So let us see how nanoparticle metagrids are useful in enhancing light extraction efficiency of LEDs. So this is what happens in a normal LED, that within, so if the light is getting generated from this PN junction, and when they are hitting the interface between the LED chip and the epoxy at an angle larger than the critical angle, light gets reflected. Now that is the critical angle loss. Now, and if the incident light has got a lower angle than the critical angle, then some portion is definitely getting transmitted, which essentially escapes from this casing and comes out to us. But there is a significant amount of reflection happening at the interface for these black cases also. So this loss is called Frannel loss. Now, what you can do, you can use nanoparticle metagrid in a very smart manner to effectively cancel out this Fresnel loss. So physically, they will be positioned like this on top of the LED chip, okay, into the casing layer. And this is how they will look like. So the bottom layer is the emitter layer, and this is the epoxy casing. And in between, you will have a nanoparticle array, and you can model it using nanoparticle array equivalent film. So what will happen in this case, some light will get reflected from this film also. And if you are able to destructively interfere that light with the light that is getting reflected at this interface, you can cancel out the reflection and you can enhance transmission. Okay, so that has been seen here that, for different gap sizes. So this dotted line tells you the transmission from a typical LED interface when no nanoparticle is there. And when you can form a nanoparticle layer, nanoparticles are silver nanoparticles of radius 20 nanometer. They can be placed at a height 2 from the interface and normal incidence. These are different gaps. So you see, when gap is say 20, you see this the dotted line, and with nanoparticles you are able to get much higher transmission. And when you zoom it and match it with your analytical, that is a theoretical method and simulation, you can see that they are very close to each other. And this is something interesting, that normally without the nanoparticles, you get only this much, which is 84, 85% of, I think it's 87% of transmission. But with nanoparticles, you can go up to 95%, 96%, and so. So more number of calculations can be done, and optimization allows you to get this transmission level up to 99.9, okay, or 99.5%. It means you can extract all the photons that are getting generated in the LED by using this nanoparticle metagrid. We have filed a patent for this. I hope the technology will be available soon for some commercial usage, but that is going to be very interesting application of nanoparticle plasmonics, or you can say nanoplasmonic metamaterials for a practical applications, for a practical application like enhancing light from LEDs. I'll also show another work of my student where we are working towards electrotunable all-weather smart windows. So this is not completely aligned to the theme of this workshop or presentation, but still I would like to tell you what nanoplasmonics can do here. So these are basically metal dielectric metal layer, okay, and you have incident solar and non-solar radiation. So using this metal dielectric metal layer, and you can apply different voltages to the metal, and you can put a electro-optic polymer in between, and you are able to tune the transmission spectrum for different applied potential. So say if you have a minus 15 volt applied across these metal electrodes, you are able to get a very high transmission of visible light, and you are able to block IR. So where it will be useful? Say in Delhi, Rajasthan during the summer, where you want only light to enter your room, not the heat, you can actually apply this kind of potential to the metal dielectric metal setup that can be used in glasses of your buildings, that can be used in vehicles, cars, aeroplanes, everywhere. So these are basically spectrally selective filters, nothing else. And they are based on metal dielectric metal design, and they are electrotunable. When there is no voltage applied, you get a transmittance that is peaking around say 780. And if you want to only allow heat and block light, you can apply plus 15 volt, where you can change the transmission peak towards higher wavelength. So you are allowing IR, that is heat, to enter, and there is a dip in your visible wavelength range. So there is a, you are able to block light. So these are also different types of all-weather electrotunable smart windows. Why I showed this here, because you can design nanophotonic devices for high-speed communication based on this kind of electrotunable feature. This is one application, but then as I told you, these are nothing but electrically tunable, spectrally selective filters, nothing else. So they have much more applications in optical communication field as well. Okay, so this is something very similar. So I'm skipping this. And coming to the theoretical part, so you can actually again apply transfer matrix method for your metal dielectric metal interface, and you can obtain what is reflection coefficient and transmission coefficient. So you can understand that this transfer matrix method is a very, very useful tool for modeling all these different multi-layer structures. You can also use transmission line method, okay, and you can do the impedance matching and finally come up with what is, reflection coefficient and transmission coefficient. You can also utilize Fabry-Perot interferometer conditions and find out what is the, uh, resonance wavelength that each of this metal dielectric metal structure will suffer. These are what? AU gold, DAST gold. This is AG, DAST, AG. DAST is the electro-optic polymer. So I am showing here the results for gold, electro-optic polymer gold, then silver, electro-optic polymer silver. This one is for copper, electro-optic polymer copper. We also tried with ITO, azido alone. What is ITO? Indium tin oxide. Azido is aluminum doped zinc oxide. These are new, transparent conductive oxide which are coming into more applications. But as you can see, they do not have that good tunability as the traditional plasmonic materials. Okay. So this is how I show the results, that what we calculated from FEM, which is the light blue line, and you see transfer matrix method, they are perfectly matching. If you see transmission line theory, that is also giving you the perfect calculation of the resonance peak position. It means that whatever theory or the structure that we are simulating and designing, they are actually backed by both simulation theory and sometimes experiments. So these electrotunable devices are possible, and this is the possibility to take them further into the field of high-speed communication, optical communication, where tunable devices can find more and more applications. Okay. So I'll stop here and I will start taking questions. So thank you everyone for your attention.
Any questions from participant side? Any
Good
question?
afternoon, sir.
Yes.
Ma'am.
Sir, is there any open source software to do such kind of simulations, sir, other than CST? There are proprietary, no? Is there any free?
Yes, CST console are proprietary, but there is FDTD softwares are there
Yes.
which are open source. So you can actually look for FDTD software, which is the time domain simulator. There you will find couple of options to do the simulations. Okay.
Okay.
So
Those results will be considered like okay for publications and all. If you do
yes,
use
as
those.
long as you back your simulation result with theory, you are able to show that your theory and simulation are matching. Okay, then they are considered as good results. Nobody will stop you in that case, right? So as you can see in our case, we have mastered this transmission line theory in such a way that they actually give you a perfect overlap. So we understood, and over the years, so this is why I told you that the work I present here is the work I have done during my postdoc at Imperial College London. So after that, I started in 2015, I believe. From that 5-6 years, we have improved the theory slowly, that you see this kind of, you know,
Yes.
amazing match is found, right?
Yeah.
So once you do that, you will be able to so publish your work.
Okay.
And instead of doing simulation from FEM FEM, which is usually done by COMSOL or CST, which are proprietary software, you can also try FDD. There are a couple of open source FDD softwares. Okay, and then it should be fine. Thank you.
Anyone else? I think there is no more questions from our participants now. So
Okay.
thank you, Dr. Siddhar. Yes, any question? So we thank you, Dr. Siddhar, for sharing your work and extensive, actually, we have seen your slide, extensive research is there. So I believe people are writing in the chat box also that it's very excellent session. And thank you so much for
ma'am.
sharing your
Everyone.
knowledge.
Thank you, ma'am, for this
And
opportunity. Yeah.
thank you.
Yeah. Thank you, everyone. Have a nice day.
Same. Thank you.
Thank you. Bye.
So our tomorrow 9:30 we have another session, the first session for the third day. So we'll join at that time. Okay, thank you all.
Okay. Thank you, everyone. Bye.
Thank you, ma'am. The link will be same, no, ma'am, for tomorrow.
Yes, the link will be same. And if you have any doubt, you can mail me anytime.
Okay. Thank you.